Hey guys, day 11, calculus. Hope you're ready for it. For today, we're going to be continuing our conversation about limits and kind of starting to talk about some of their basic properties. We're going to focus today on analytical limits, which ironically is what you did last time. We're going to talk about how to identify and name a limit and then how to evaluate it using a very specific process. Let's take a look and see how you guys do. Last time I hope the instructions were clear and you did all the pieces. There weren't a lot of problems, but they had a lot of pieces to them, especially if you're not handy with a calculator. So make sure you take your time and get your stuff done. Okay, let's take a look. First of all, let's we defined limit last time, but let's talk about how to write a limit. Let's say I have a function f of x where I want to evaluate as we get close to, let's say, 3. So how do we write this as a mathematical statement? So you might have noticed in mathematics that a lot of stuff is written out, like by hand. There's a lot of ways to write. Like instead of saying the word addition or add, we write the symbol plus, right? Instead of saying the function in relation to x, we write fx, right? We use symbols a lot in mathematics to interpret a lot of information very quickly. That trend does not stop. In fact, in calculus, sometimes some people think it gets too out of hand, but it's important to note that anytime you talk about a function, you can talk about the limit using the following notation. So we use lim to indicate we are doing a limit. We identify what we're approaching using these two symbols. We tell what variable we're approaching it with, because that's important later, and then what value we are approaching it from. So what this statement means is we are taking a limit. This is the variable we are plugging into, and this is the number we're going towards. And then we either put in f of x, or we could, of course, write out the polynomial or equation in question. And what this statement reads as is, this is the limit as x approaches 3 of f of x. Similarly, if I was to write out limit as x approaches -2 of x cubed minus 4 is equal to, we would write this as the limit as x approaches -2 of x cubed minus 4. And while it's not common, because most calculus is done in single variable calculus, you can do it with other variables too. Like if you had the limit as y approached 0 of xy minus 2x plus y, notice how what's in the limit typically goes in parentheses. This is to make sure that it's not like the limit of just this piece or just this piece. It's the limit of the entire thing. This is an operation kind of like a natural logarithm, or if you're done trig, a cosine. Like it's an entire operation. This is one mathematical statement. The limit as y approaches 0 is one thing, and this is simply the equation we're doing it to. We would say the limit as y approaches 0 of xy minus 2x plus y. And so that's how we write a limit and how we read a limit. And so notice there are some significant parts. You have to look at the variable in question, you have to look at the number you're going towards, and you have to know what the function is, either as an undefined function or as a defined function. So for today, we're going to focus on what's called the analytical approach. What this means is we're going to use numbers that get us close to whatever number we have in question. So let's look at these three limits and talk about how to do an analytical approach to them. If I want to do the limit as x approaches 3, how we can do that limit, you saw last time, is by doing a table. x is going to be what we're plugging in, and f of x is what we're going to be getting out. Now, we want it to approach 3. I'm going to give myself some space here. So I'm going to put 3 here kind of in the middle. How do we approach 3? Well, there's a couple ways to do this. You have to approach it from both sides. So there's numbers that are less than 3, and there are numbers that are greater than 3. We need to approach it from both directions. This is to give us a clear indication that we are in fact approaching one distinct number in the middle here. So how do we do that? Well, the most common way is to test values that are close with a pattern. So you would do 2.9, 2.99, and 2.999. It's a terrible 2. So notice how 2.9 is very close to 3, but 2.99 we can all agree is closer. And 2.999, as I'll call it, is very close to 3. So each one of these, when we plug it into our function, would get us just a little bit closer to 3 without actually looking at 3. Think of limits. This is a great little visual aid. Limit is kind of like a solar eclipse. I can spell eclipse, maybe. Close enough, it's Thursday. Think of it like a solar eclipse. You're not trying to look directly at 3, you're trying to look near 3. Okay? You're using devices to get close to it, to get around it. You're not trying to look at 3, you're trying to look close to 3. Okay? Now, from the top, it's a similar but different process. You could do like 3.1, 3.01, and 3.001. You notice that each of these is just a little bit closer. Now, what I want to point out this one is our number minus 0.1. This one is our number minus 0.01. This one is our number minus 0.001. This one is our number plus 0.001. This is our number plus 0.01, and this is our number plus 0.1. And so notice how we just follow a pattern to get close to that value. The reason why that's really important is because, well, if the numbers are weird, this can be harder to visualize, and so these little blue markings can make it a little bit simpler to understand if you're looking for it. Let's look at the next one. If I want to do the limit as x approaches -2, what I need to do, if I'm using the analytical approach, is start by making my table. Now, -2 is going to go here in the middle. Now, I need to choose values to the left of -2 and values to the right of -2. Now, a calculator is helpful here if you're not comfortable with positives and negatives, or you could, get comfortable. That's not an insult. Do it. So, this first one should be my number minus 0.1. Well, -2 minus 0.1 is -2.1. My next box is my number minus 0.01. -2 minus 0.01 is -2.01. My third box is -2 minus 0.001, which is -2.001. If you don't believe me, use a calculator to check yourself. And so these numbers are all distinctly less than -2, right? They're farther to the left on like a number line. And that's one way to think about these, is like a number line. Right? Here's -2. We're picking, -2.1. They're picking a number that's really close, -2.01, and then a number that's even closer still. Like, we're getting very close. Okay? That's the goal of these numbers, but they are all to the left. And notice they're in a distinct order. This is the farthest to the left. This is slightly closer. This is closer still. Then we get into the middle, and we can go to the right as well. The farthest to the right should be that number plus 0.1. Now, -2 plus 0.1 would be -1.9. The next one would be -1.99, 1.999. All of these values are distinctly to the right of -2 on the number line. They're all close to -2, but they're all distinctly to the right. And there's an order to them, right? Each one from outwards going in gets a little bit closer to our number, which is -2. To evaluate this limit, so the limit as x approaches -2 of x cubed minus 4, what we would need to do is, well, we need to take -2.1 and plug it in. -2.1 cubed plus 4. This one would be -2.01 cubed plus 4. This would be -2.001 cubed plus 4. And the goal is to see a pattern as we approach this middle number. I need to see a pattern that is clear from the left and clear from the right, getting to one number in between. Now last time, if you did it correctly, you would have noticed that every one we did last time did not work. The middle number didn't. For some of the ones today, it might. You won't know that until you test it. But the goal is to see, how does the limit work? Okay? This one over here, same basic cube. We do -1.999 cubed plus 4. Oh wait, the equation says -4. What am I doing? Minus. That's awful. It's Thursday. What are we going to do? -1.99 cubed minus 4. Did it again. And -1.9 cubed minus 4. The goal is you should see a distinct pattern emerge, that each one gets closer and closer to this number in between. That's the goal. Let's do the next one, because this part is algebra. Like, we should all be comfortable with that. The calc part is doing this. The last one was the limit as y approaches 0 of x, y minus 2x plus y. Well, how are we going to do that? Well, we have our y, and we're going to plug into our equation, xy minus 2x plus y. Notice rather than using f of x, since it has more than one variable, I don't want to use f of x. My goal is to plug into the y's. I need values that are close to y. Now I can always use this setup. This works. Do note, this is not the only option. How many exclamation points can I put here? A lot. You could do anything, as long as it's a pattern that gets you very close to your number. My goal is to get close to 3. If I'm starting over here at -40, like, that's probably not a good way to go. It doesn't make sense. I want to start close to 3 and get closer. 2.9 is close to 3. 3.1 is close to 3. But each step in, we get a little bit closer. This is a 7-step limit, because there are 3 to the left, 3 on the right, and then the middle is our 7th. But you could do this with 9 or 11, and you could follow the same basic pattern as well. In fact, like, this isn't the only pattern you could use. Like, you could use, like, instead of -0.1, you could do -0.2 or -0.5. But the goal should be it's always getting closer and closer. If you find that you can't determine based on just these 7 steps what the middle number is, maybe you need to go to a 9-step where you put in another column here. If I was to put in another column, it'd be 3.0001 and 2 with 4 nines. That would allow me to get another set and get even closer. Like 2.9999 is so close to 3 that on a ruler you wouldn't be able to tell the difference. Same with 3.0001. Like, they're so close you could not tell the difference with a naked eye. But maybe when you use a calculator, you can tell the difference quite a bit. So do more if you need to. Let's give an example of that here. So 0, I want to, using my same pattern, subtract 0.1, subtract 0.01, subtract 0.001. So over here, this should be minus 0.1, negative 0.01. Negative 0.001. Then we add on the other side, so 0.001, 0.01, and 0.1. Again, notice how these two are just our limited number plus or minus 0.1, plus or minus 0.01, plus or minus 0.001. But notice that each one gets closer and closer to 0, which is a number we are doing in our quest. And again, to find a solution, you just have to plug these in and see what you get. Make sure you plug them in the correct variable. Every problem you have tonight is involving x's, so you don't have to worry about y cases, but it shouldn't matter. Let's look at a textbook problem. This will be your first problem in the homework, so that should be nice. Your first problem in the homework is number 9, and it states, determine the limit as x approaches 1 of x minus 2 over x squared plus x minus 6. It says to do it by creating a table, just like we last time you were given the table. This time you're asked to make one and use your result to estimate the limit. If possible, graph to see your results work. So my goal should be, 1 should begin in the middle here. Okay, I need to choose values to the left of 1 and values to the right of 1 on my number line. And I can do that by taking our number minus 0.1, minus 0.01, and minus 0.001. And then this opposite on the other side. So let's do that. 1 minus 0.1 would be 0.9. Minus 0.01 would be 0.99. And 001 would be 0.999. Over here, it would be on the farthest side, it'd be 1.1, it'd be 1.01, and 1.001. Let's see if we actually get a limit. Now to do this, I'm going to use my calculator to assist with this quite a bit. So let's pull that up. There's my TI. Get out of this window. What I'm going to do is I'm going to type in, I'm going to do it the old-fashioned way, 0.9, I guess I should do it in parentheses. So 0.9 minus 2 divided by 0.9 squared plus 0.9 minus 6. And what do I get? When I type in 0.9, I get 0.2564. Okay, that's fancy. We do the same thing now, but with 0.99 divided by 0.99 squared plus 0.99 minus 6. Okay, which gave me 0.2506. Okay, now I do the last one on that side. So I do 0.999 minus 2 divided by 0.999 squared plus 0.99, not 99, 0.999 minus 6. Now if you've done this correctly, you should notice that this is approaching a number. Now let's go to the right hand side, same thing. So I do 1.1, oops, do it correctly. 1.1 minus 2 divided by 1.1 squared minus 1.1. Oh, dang it. Oh, I love Fridays. Plus 1.1 minus 6. It says this is 0.2439. Okay, I'll do it again. 0.01 minus 2 divided by 1.01 squared plus 1.01 minus 6, 0.24937. You might be asking questions like, how many decimals do I need to go to? Does it matter? The answer is no, it doesn't matter at all, as long as you're going far enough to see the pattern. And so you may want to go to 3, you may want to go to 4, it kind of depends. I typically try to go to 4 when possible, just because it keeps myself consistent. Minus 6. Now if you look at these numbers, let's go ahead and minimize that. If you notice these numbers, the left-hand side is getting smaller over time. As we go from left to right, we're getting smaller and smaller. And what value are we approaching? We are approaching 0.25 with a bunch of zeros after it, or 1/4. What about the right-hand side? Well, as we go from right to left towards the number, remember, always towards the number, we have 2.439, 2.4937, 2.499. These are also getting closer to 0.25. Each one gets successfully closer and closer to this number. And if you were to continue, it would keep happening. And keep getting close to this 1/4 mark. The reason being, of course, is that if I actually pull this thing open and type in 1 minus 2, 1 minus 2. Oh, come on. Parentheses. 1 minus 2. Divided by, parentheses, 1 squared plus 1 minus 6. This is a successful limit. This is a good thing, because not only did my left-hand side and my right-hand side approach a value, but it's the same. This is a good limit. We'll talk about what happens when a limit fails next time, but you can imagine, based on what we've seen so far, what that's going to look like. Unfortunately, I have to go to a meeting, so that will be it for today. We only have a couple problems tonight, which should be nice, but otherwise, that's all we got. Hope you guys have a good weekend. Note these examples that I've given you here and how to create the table, specifically this one here in blue, which is the general way to make it, but remember, it is not the only option. And that'll be it. I hope you guys have a good time, and I will see you on Monday.